Hi everyone, welcome to the second of two videos going through some past exam questions on transition metals, redox titrations, just sort of other sort of awkward questions really. So again, this question, they've given you an enormous amount of information. I'm going to actually skip over all of this and go and look at the question first. I think this is a useful tip that I'd give you is if you read or you're going to just read this and confuse you, so you're going to go, I don't know what the hell's going on here, there's all stuff going all over the place. I wouldn't bother. Go and read the question, then go back. You are going to have to read through all of this, right? You need to make sure you've read it carefully, but read it after you know what you're looking for, okay? Rather than just reading the whole thing and getting bewildered. You go, right, I'm looking for, what does it say? Write an equation for the reaction between iron 3 oxide and concentrated hydrochloric acid that occurs in stage 1. Oh, okay, I just need to look at stage 1 then. Right, and it makes it manageable. So it's a reaction between iron 3 oxide and concentrated hydrochloric acid. So we just need to look at stage 1. Hydrochloric acid is added, iron 3 oxide reacts to form a solution containing Fe3 plus ions. Okay, so if we've got iron 3 oxide, so that is going to be Fe2O3, isn't it? So that's 3 plus and that's 2 minus. Concentrated hydrochloric acid. So those two react together is going to make iron chloride, isn't it? And water. Yeah, an acid and a base makes a salt and water. So it's iron, and it says it's containing Fe3 plus ion, so it's going to be iron 3 chloride. So it'll be FeCl3 and water. And now I just need to balance it. So I've got 2 ions, so that's going to be 2 there. So 6 chlorines, so 6 hydrogens, so 3 there, 3 oxygens, 3 oxygens. Okay, so that's not too bad. Right, now it wants us to write equations for the reactions involving ions in stage 2 and 5. Okay, so do you see what I mean about don't read the whole thing? You're actually just doing it in stages and it makes it manageable. So stage 2, an excess of tin 2 chloride is added. SN2 plus reduces Fe3 plus to Fe2 plus. And excess SN2 plus is removed. Okay. Actually, we can link this to the redox potentials here. So this is these two, isn't it? This is SN2 plus is reacting with Fe3 plus. So it's these two reactions happening. And you can see this has got 2 electrons in it, and this has only got 1, so we have to multiply this one by 2. So we're going to have 2 Fe3 plus the SN2 plus. Okay, this has got the more positive electrode potential, so that's going to be as a reduction, as it's written. This is less positive, so it'll be an oxidation, and this reaction will happen backwards, won't it? So that'll make SN4 plus. Yeah, that's why we've got to use this. It doesn't tell us that SN4 plus is produced up here, does it? So the way we can work that out is by doing it from here. And we're going to get Fe2 plus because this is reacting that way. That's reacting the opposite way. And we're going to get 2 Fe2 plus, aren't we? Okay, to make this balance, check the charge is balanced. 6 plus and 2 plus is 8 plus and 8 plus on that side. So that's nice and easy. And stage 5, the solution in the conical flask is titrated with potassium dichromate. Fe2 plus is oxidized to Fe3 plus. Right, so again, we're going to use these electrode potentials. Here, it's saying Fe2 plus is oxidized. Yeah, because the dichromate is an oxidizing agent, isn't it? And that's got a more positive electrode potential. So that's going to be the one that's as a reduction. It's going to react as it's written. This one is the least positive one. So that's going to be oxidized. It's going to react backwards. Okay. And then if we're going to combine these two together, this needs to be multiplied by 6, doesn't it? So that the electrons balance out. So we're going to have 6 Fe2 plus. And then this reaction is happening the right way round. So the dichromate ions plus the 14H plus. The electrons will cancel out. It's going to give us 2 Cr3 plus and 7H2O. And then we're going to get Fe3 plus, and that's been times by 6, hasn't it, to make the electrons balance. Again, it's worth checking the charges. 6 lots of 2 plus is 12 plus, and 2 minus, that's 10 plus, and 4, so that's 24 plus on that side. And I've got 6 plus here, and 6 lots of 3 is 18 plus 6 is 24. So we've got 24 plus on both sides. Okay. So the key to that question is using these electrode potentials. Yeah, don't try and write this yourself. That's why it's only worth 2 marks here, right? If we were going to have to write this full redox equation, then that's going to be 2 marks by itself, right? We'd have to do oxidation numbers and all the rest of it and balance the oxygens with water, and we didn't need to go through that whole process because they've done most of it for us, look. So use the electrode potentials from there. Okay. Right, this question carries on, and it then asks us to calculate the percentage by mass of iron in the hematite ore. Okay, what? Okay, so now is the point where we're going to actually have to go back and read all that information. So let's go back and work out what this was all about then. Right, so hematite is the ore of iron. The percentage of iron in a sample can be determined using this method. Okay, so that's what we're trying to do, isn't it? Work out the percentage of iron by mass in this hematite ore. So hydrochloric acid is added to this hematite. The iron 3 oxide reacts and it makes Fe3 plus ions, right? That's this reaction that we wrote down in stage 1. Then we do the reaction that we wrote down in stage 2. So that takes your Fe3 plus and reduces it to Fe2 plus. And it's diluted and made up in a volumetric flask. Okay, so we've made up a standard solution then of Fe2 plus ions. 25 centimetres cubed sample of this is pipetted. So we're going to do a titration now, aren't we? Standard solution, take a bit of it, put it in a conical flask, and then titrate it against potassium dichromate. And that's the reaction that we just did in step 5. Okay. This is repeated to obtain an average titer. Okay, so again, if you watch the previous video here, the trick I would say now is find all the numbers, because the numbers is where we're going to have to do something, right? So that's relevant. We've got a number here. And we're going to have to do something with all of these numbers eventually. Okay. And then the other trick that wasn't really relevant in the previous question, but works quite nicely with these titration questions, is that most of the time with these questions, where you want to start is at the bottom and work your way back up to the top. So you're probably going to go through these numbers in that order from bottom to top. Probably. Doesn't always work out as simple as that, but that's a good place to start. So we got an average titer of 26.5 centimetres cubed. That was the volume of whatever was in the burette, wasn't it? Which was the potassium dichromate, right? Because the other iron 2 plus sample was in the conical flask. So that was the volume of this that we used. So this is where we're going to start. Like I said, the 2 numbers at the bottom. Yeah. So use these 2 numbers and work out the moles of potassium dichromate. Okay. So we're going to do 26.5 over 1,000 to get it into decimeters cubed. And we're going to multiply that by the concentration, which was 0.02. Right, let's work that out. 26.5 over 1,000 times 0.02. So we got 5.3 times 10 to the minus 4 moles of, that's the potassium dichromate solution. Okay, now we've got that. Now we can use our equation that we wrote. And this is sort of, going by, this is a titration calculation, right? But it's also just a chemistry calculation. What do we do in chemistry calculations? Almost all the time, it's work out the moles and then use the ratio in the equation, isn't it? So that's what we're going to do next. Use the ratio in this equation that we wrote down earlier on, right? That's why they made us do this first. So we know how many moles of this we've got, and we want to work out the percentage by mass of iron, don't we? So we want to work out this. So we're going to now times this by 6 to get the moles of Fe2 plus. Yeah. So we're going to say it's a 6-to-1 ratio. So 5.3 times 10 to the minus 4 times 6 is 3.18 times 10 to the minus 3 moles of Fe2 plus. Okay. So we're getting somewhere. We now know how many moles of Fe2 plus we've got, and we want the mass of iron, don't we? So let's just go back to our information and start, like I said, working our way back up the question. So we did that, didn't we? We've done those two together. Okay. So that is the mole. We got the moles of Fe2 plus. Right. The next number we get to is this 25 centimeters cubed sample. Okay. So we could work out the concentration, but that doesn't really help us. We want to get mass, don't we? These two numbers are important then, because this is a 25 centimeter cubed sample of the original solution. Okay. So this number of moles that we worked out, we need to be careful. This is the number of moles of Fe2 plus in 25 centimeters cubed in that sample. Okay. The number of moles in the original 250 centimeters cubed would be 10 times as much, wouldn't it? So that's what these two numbers are here for, is to remind us that we're going to have to now times by 10 to get back to how many moles are in that solution. So if we use those, we're going to now times by 10. Okay. So if we times by 10, that's going to give us 3.18 times 10 to the minus 2 moles of Fe2 plus in the 250 centimeters cubed. Okay. And that's important because that 250 centimeters cubed is where this original 3.25 grams came from. So now that is the right number of moles we can use. We can now multiply this by the atomic mass of iron to get grams, and then we want to do that mass as a percentage of this. Okay, so hopefully we get a mass that's less than 3.25. Okay. So on my calculator, I'm going to do this times by 10. I hadn't done. And so now I'm going to do 3.18 times 10 to the minus 2 moles times by the atomic mass of iron, which is 55.8. Okay. And that's going to give me a mass in grams. So I've got my number, times it by 55.8, 1.77, okay, grams of iron. And it wants the percentage by mass. So now I just need to do that as a percentage of the mass from here, this 3.25. So now I'm finally using that number. And now I can be pretty confident that I'm done, right? Because I've used every number they've given me in the question. Okay. We didn't actually use this in a calculation, this 25 to 250. But we did account for it, didn't we? So we have had to do something with each of these numbers, if you like. So now I want to do that as a percentage, okay? So the percentage by mass is going to be 1.77. Well, let's do the whole number, 444 over 3.25 it was, and times by 100. So take that whole number, divide by 3.25, times by 100. And we're going to get, does it say anything about significant figures in this question? I don't think it does. No, let's just have a look at the values here. What's an appropriate number of significant figures? Well, we've got 3 significant figures, 4, 3, lots, 3. Okay, so the smallest number of significant figures we've got is definitely 3, isn't it? So let's do it to 3 significant figures. So let's call it 54.6%. Okay, and that's our answer. Okay. So hopefully, again, there's one of those questions where there's lots of information here. But again, things I want to give you sort of how to approach the questions, right? Is find the numbers, work your way up from the bottom, usually. Don't read the whole information until you have to. Go and find what you're looking for first, so you don't bewilder yourself with all the information. Please be careful that you do definitely need to make sure you've read it all, right? I'm not saying don't read it. I'm saying read it when you know what you're looking for. And then just laying it out, like look at how I've laid this out. Every time I've written values, I've put units so I know what I'm doing. I've worked out a number and then I've written down exactly what it is that I've worked out for my own benefit. Right? I haven't just got a number, I've got the moles, I've got what chemical it is, and even in that case, what volume as well. And I think that's just really important for you to keep track of what you're doing, because otherwise you just end up with numbers all over the page. Right, and then finally, the last question here, what's it saying? It says, aqueous potassium manganate is not suitable for titrating. Okay, you could use that. That's an oxidizing agent, the same as potassium dichromate, but they've used potassium dichromate here. Suggest and explain why potassium dichromate is suitable, whereas potassium manganate is not suitable. Okay. So why would that be? That's a bit odd. Okay, so again, here's how we're going to approach these questions. We're going, well, I don't know. I was wondering about the colour changes, but that doesn't really matter here. The manganate, you get that purple colour change, don't you? That's not a problem. If we go back and look at information they've given us in the question, right? If we're stuck, go back and look at the question. We go back to here and we find, there's an electrode potential here that involves manganate ions. It's a bit odd because we haven't had to use manganate ions in this question at all, right? All the way through this bit, we used the tin and the iron for doing that equation. We used the dichromate ions in this one. So we've got this chlorine as well. So why have they given us these two half equations? That's a bit suspicious, right? So what's it saying here? Right. So what's going to happen here is this manganate one is even more positive. Where are we? Where's the iron one? So that should be okay. Okay, I see the problem. So the other thing is, sorry, I was struggling there for a minute myself. Again, I was trying to work out why have they given us this chlorine. We can see why this is here. Why is this chlorine electrode potential here? That doesn't seem to have anything to do with anything, right? I can now understand why this one's here because that relates to this question. What's this chlorine electrode potential here for? Where does it mention chlorine in this question anywhere at all, right? And it does. Again, usually they haven't given you information for no reason, right? Where does it say about chlorine? That's the key to this question. Right, it mentions using an excess of concentrated hydrochloric acid here. Okay, so we end up with this chlorine here. So we've got chloride ions at the end of stage 1. Those chloride ions are still going to be around, aren't they? We added tin chloride again, so there's still chloride ions. There's still going to be chloride ions in this solution, right? They're not relevant in the reaction, so we haven't bothered mentioning them. But the problem here is, if we use manganate has a more positive electrode potential than chlorine. So the manganate would react with chloride ions. This reaction is the more positive one, so it would be reduced. The chloride ions would be oxidized. So instead of the manganate oxidizing the iron, it would also oxidize the chloride ions. Okay, and that's going to mess up our reaction. The dichromate ions have got a less positive electrode potential, so they are not going to react with the chloride ions. Yeah, these would react the other way around, but we haven't got any chlorine, the element, so it's not going to be a problem. So this is what the problem is, that manganate would oxidize the chloride ions, whereas the dichromate ions won't. Okay, that's a horrible little question. That's really sneaky. So what we want to say here is then that the electrode potential for the manganate is more positive than, and I'm just going to write the electrode potential like that, than for Cl2. So MnO4 minus ions would react with Cl minus ions in the solution. Okay, if we go back to that again, if we have got Cl minus ions in our solution, because it's come from the HCl from up here, and it's also come from the tin chloride, so instead of manganate reacting with our iron, which is what we want, it would be reacting with the chloride ions, okay, because this reaction has a more positive electrode potential, so it would be reduced, it would react that way. This one would react that way. So this would react with that. With the dichromate ions, it's less positive than chlorine. So this would not react with the chloride ions. If you did, you'd get chlorine reacting with chromium-3 ions. But that's not a problem. We haven't got chlorine in our solution. We've got chloride ions. So these two reacting with each other would not be a problem because it would actually react the other way around. So that's fine to use. That's not fine to use because you would get this other reaction. So it's a 2-mark question here. So we're probably going to have to also write that the electrode potential for the dichromate ions is less positive than the electrode potential for Cl2. So the dichromate ions would not react with Cl-. So that's not something we have to worry about with the dichromate. Okay. That's a horrible little sneaky question. But I won't worry too much about that. The main focus is make sure you can do this 5-mark question, and being able to do that one.